And I'm now recording. Excellent. Okay, so yeah, welcome everybody. Let me just share my screen. And jump over to the PowerPoint. Wonderful. Okay, so thanks a lot. So I really appreciate all of you for having the guts to take this relatively complicated sounding course on Introduction to Quantum Algorithms. So the key point, what I really want you to be able to get out of this course more than anything else, is I really want you to be able to understand the computational model that that underlies quantum computing. And in particular, I'd like you to really be able to understand how the art of quantum algorithm design ends up working and where the power of that quantum computers have relative to ordinary computers, where that power ends up emerging. So those are going to be the key things. And we're going to be looking at this through a bunch of different lenses. Primarily, we're going to be looking at, results on what the gate complexity is to solve particular tasks using quantum computers, as well as looking at query complexity, which is, again, is just the number of times we need to access particular subroutines in order to be able to solve these problems using quantum computers. And also, I'm going to spend a little bit of time talking, about ideas like quantum complexity theory, not terribly much, but a little bit, and also talk about how some of these lower bound techniques can actually be used in order to prove the best known lower bounds for query complexity for actually ordinary algorithms. Because one of the beautiful things about quantum computing is it provides a framework that encapsulates everything that we know about ordinary computing. So the extra freedoms sometimes actually make it easier for us to prove things about algorithms in the larger setting that ends up allowing us to understand the restrictions of ordinary algorithms. And this has actually led some people to say, to suggest that even if the world was entirely non-quantum, some of these tools are so powerful that actually, or computer scientists might have had to have invented quantum computing anyways, in order to provide the mathematical tools needed to prove bounds on some functions. So these are the sorts of things that I really want you to get across. And in particular, the one lesson, if you learned nothing else from this, it's just that quantum computing is not necessarily vastly more powerful than ordinary computing. It's different. And for some problems that end up fitting inside this paradigm naturally, we can have huge, as in exponential speedups or polynomial speedups of the best possible ordinary algorithms for solving these tasks. However, for other problems, we actually can't get a substantial speedup. So one of our aims is to try to understand why and how and understand how we should best apply quantum computing in order to solve particular tasks. So here's the syllabus, because I've been told that I have to read the syllabus to folks. Basically, the TLDR is if you do work, you get grades. So we'll be going off of bi-weekly assignments. So the assignments will be relatively long, but they'll be due once every 2 weeks. They'll be due Friday by midnight, submitted via email. My preference for the submissions would be LaTeX files for everything. However, if for one reason or another it's inconvenient for you to do LaTeX, having handwritten scans is perfectly fine for everything. Yeah, Philip, you got a question?
Oh yeah, would you provide us with a LaTeX template, or just whatever we can find is fine?
Hey, any template that you like that's readable is good by me.
Thanks.
However, yeah, what I'll do is when I typeset the first assignment, if you feel like using the same template that I used in order to, do the assignment and just like fill in text after the question, you're more than welcome to do that. Any other questions? All right, so then the next thing I wanted to mention is, again, because of the uncertainty that we have about whether or not in-person education is going to be able to continue the entire term, I wanted to make sure that there was nothing that is set up in the syllabus that explicitly mandated that anybody be on campus at any time. So for that reason, we're doing a take-home midterm and a take-home final rather than in-person examinations during this. Again, these all examinations are to be done independently. So no collaboration on those whatsoever is permitted. However, collaboration on the assignments is permitted, but we require that you individually do any of the write-ups. So even if you talk to somebody on this, please no copying and pasting it. At least go to the effort of writing up the joint discussions that you had individually. And that basically, I think, is more or less it. If any of you have any special requirements or any extra assistance that you need that I can provide, please let me know as early as possible. I'm more than accommodating, but you know, I kind of need to know as early as possible if there's some way I can help you. So just reach out, and I'm more than happy to help you if something ends up coming up. Any questions before we actually get started? Yeah, Philip.
Sorry, I just have a question about the textbook. Do you recommend we get a paper copy, or will we have access to that online?
So the library, I believe, has access to Nielsen and Schwang. I would strongly recommend against doing a Google search and searching for Nielsen and Schwang 10th anniversary edition, because you might accidentally end up finding a bunch of illegal copies that are available online. So I would strongly, strongly recommend that you don't do anything so unethical. But but otherwise, getting a copy from Amazon, the bookstore, or some other source would be good. One thing, though, you did that is related to this that I wanted to bring up is why I wanted to teach this course in the first place, right? One of the main reasons why I really want to teach it is because the textbook, and this is the standard textbook that everybody learns from in this course. This textbook was written and with a small update in the year 2000. Okay. So, you know, we've had an entire war in Afghanistan pass before, in between when when the book was made and now. And since then, unsurprisingly, quantum computing has changed radically. And so this textbook, while it's an amazing textbook, and while it covers the foundations of quantum computing better than any book that I know of, there's actually a bunch of topics that aren't covered whatsoever in this. And these topics are vitally important in order to understand modern quantum algorithms. So that's the reason why I really was passionate about teaching this course, is because I want to teach you these new ideas as well as the fundamentals that are discussed in this book, because these new ideas give better ways of thinking about quantum algorithms than the methods that are discussed in Nielsen and Schwang. But sadly, that's the best textbook that exists at the moment. So I'd recommend that that one way or another, you get yourself a copy of the textbook, and the library, I believe, has digital copies that you can use. But it's a good book. A physical copy isn't something that I think is really harmful. Yeah, so anything that floats your boat, really, when it comes to getting access to these course materials.
Hi, Nathan. Are you planning to write a new book?
Oh, writing a new book, unfortunately, I'd love to, right? But, you know, unless I end up getting, you know, like a time turner, Harry Potter style, I don't know how I'll be able to fit in the time in order to be able to do it. At some point, you know, if research starts slowing down a bit, I'd love to. But for exactly this reason. But until that happens, yeah, the best that I'm going to be able to do, I hope, is eventually get around to generating some good course notes.
Yeah, I think so.
Any other questions? All right, cool. Then in that case, let's get started. So right. So the first question that I think we should address is, well, why talk about quantum computing, right? And there's a number of different reasons why people are interested in quantum computing. The first, the most significant reasons, or for most people, are speed ups. Okay, so this is one of the things that's caused companies like Google and IBM to invest billions of dollars in the development of quantum computing. There's certain problems that quantum computers can actually solve in exponentially fewer operations than the best known classical algorithms. One thing in terms of nomenclature that I wanted to mention is that it's common parlance in quantum computing, unfortunately, to kind of refer to ordinary computing, the type of computing most of you are really familiar with, as classical computing. And we do this because of the physics influence that ends up coming in. Because people who come from a physics background refer to everything that doesn't require a quantum description as classical. So it's not meant as a derisive term, but you'll periodically hear me refer to ordinary computing as classical computing. So in any case, quantum computing offers speedups, in some cases exponential speedups, over the best known classical algorithms. And these speedups famously have been shown for factoring. They've been shown for quantum simulation, as well as particular problems in linear algebra, such as matrix inversion, for example. And so these speedups are in fact exponential. So the time required to do some of these things, like say we were to take a look at a problem in quantum simulation and we wanted to simulate a molecule, a relatively simple molecule on the order of 100 electrons that are interacting. It turns out that the size of the space that you need to keep track of ends up scaling exponentially with the number of particles that you need to track if we take a look at quantum dynamics. So the cost of doing this is kind of on the order of like order 2 to the 100 if we want to do this exactly on an ordinary computer. But a quantum computer can do this in time that goes kind of like order n to the 4th, which in this case is like 100 to the 4th power. So that is pretty amazing. And so there's some problems that we end up getting in physics that are vastly easier to simulate on a quantum computer. Similarly, factoring is something that can actually be directly mapped to a quantum problem, which was the totally surprising insight of Peter Shor. And this ends up causing quantum computers to be able to break RSA in polynomial time. So in the event that a scalable quantum computer ever gets built, then any crypto scheme that ends up depending on assumptions of the computational hardness of factoring ends up actually kind of going out the window if ubiquitous quantum computing starts becoming a thing. So there's a lot of profound changes that quantum computers, once they come of age, will end up making. There's also smaller speedups like that we can end up getting, where we can get quadratic speedups for a wide range of problems. And most generally, we can get a quadratic speedup for any problem in NP. So anything in the complexity class NP, which are the set, which is the class of problems where the yes instances to a decision problem can be efficiently checked using a deterministic Turing machine. So we can get quadratic speedups over the best classical algorithms for a host of really important problems, in addition to these exponential speedups. So from a practical perspective, this is why people spend so much money in quantum computing. But to me, this isn't why I'm interested in quantum computing whatsoever. This is cool, right? But for me, the real interesting bit about quantum computing ends up coming in because I want to understand fundamentally what the computational power of the universe is. So we believe that the universe is governed by physical laws, right? And how the universe fundamentally works is, if you think about it, right? It takes a bunch of, say, particles in, and then it will set output a new combination or a new configuration of particles coming out for any physical process. The question is if we think about this taking place on, say, like a gigantic laptop, which I think probably looks something like that. The question is, what kind of computational power would that machine have to have in order to be able to simulate the natural dynamics that we see in nature? Or in other words, if the matrix were true, what kind of computational power would would the AIs need in order to be able to trick us into thinking that the universe obeys physics rather than is being simulated on some kind of a computer? And so this kind of boils down to this long-standing question that ends up existing. And this question is known as the Church-Turing thesis. And the idea behind the Church-Turing thesis is, at least the strong statement of the Church-Turing thesis, is any physically realistic model of computing can be simulated efficiently by a Turing machine. Okay, this thesis over here, it's not proven. Nobody knows if this is true. So this is kind of like a religious belief that many people who adhere to it have. They'd like to believe that everything in the universe that's physical, like because we can envision any process that transforms information into new information as being a computer of a sort. And any computational model that we could come up with that would be, according to the Church-Turing thesis, should be efficiently simulatable on a classical Turing machine. However, the existence of these speedups causes this belief to come into question. And so the real question is this true? Or instead, do I need to replace a Turing machine with a quantum Turing machine? Okay, and we have a number of good pieces of evidence that I'll be discussing in this course that the original vision of the quantum Church-Turing thesis, that, where we could think about the universe as essentially just being a gigantic Turing machine, seems to be unlikely because of the fact that we have these speedups that end up existing that seem to require or seem to provide exponential advantages for quantum systems, or end up suggesting that quantum systems end up really requiring exponentially many gate operations for a Turing machine to be able to simulate. So that, for me, is why I'm most interested in it, because I really just want to understand what opportunities and what restrictions the laws of physics end up creating for computing. So these are kind of like the two big reasons why we do it. But really, at the end of the day, if I'm honest, what makes me really kind of continue to do and love quantum computing is this extra fact that linear algebra rules. All right, I really like linear algebra. So, and fortunately, the language of quantum computing ends up allowing us to think about all of quantum mechanics, all of ordinary computing in a very convenient linear algebraic language. And that's going to be what we'll spend the first bit of this course dealing with. Because before we can end up jumping into explaining why these speedups are possible, I need to explain quantum mechanics to you guys in a way that, that computer scientists will be able to understand. Fortunately, because it's all linear algebra, I really only need to discuss it from the linear algebraic perspective. The the way that we're going to be going about this is as follows. Okay. So the way we're going to be going about this, let me, yes, this will be a smart way of dealing with it. Okay, the way we'll be going about this is kind of hierarchical. What we're going to start with is we're going to start with ordinary computing. Okay, just to make sure that everybody's on the same page. Then I'm going to talk about a alternate way of doing ordinary computing, and this is what we call reversible computing. Okay, then once we've described reversible computing, I'm going to generalize it a little bit further. And then I'm going to talk about probabilistic computing, or specifically probabilistic reversible computing. And so this is exactly the same thing, but instead of the bits being used, being considered deterministic, like in a definite state of 0 and 1, we now allow our bits to be in a probabilistic mixture of 0 and 1. Then finally, once we have that, this will allow us language that we can end up using to conveniently describe quantum computing. And the reason why I'm doing this is because of the fact that often people end up liking to think that quantum computing is kind of logically equivalent or just straightforward generalization of ordinary computing. However, the most natural and connection that ends up existing is between probabilistic computing and quantum computing. So if we want to compare, the reason why I'm bringing this up is that actually in the history of quantum computing, people ended up making a lot of mistakes by believing that quantum computing for some problems gave an exponential speed up over classical computing because they just compared quantum algorithms to deterministic algorithms that were being used for particular tasks. But it turns out that even though the quantum algorithms provided an exponential advantage over known deterministic algorithms, it actually in some cases will only provide a polynomial advantage over probabilistic computing. So that's one of the reasons I'm building it up, to make it clear what the connections are, and also to make it clear how you ought to think about comparing and contrasting ordinary computing to quantum computing, because the best link or the best analogy is through this probability connection. All right, so before I get started on ordinary computing and reversible computing, anybody have any questions?
Yeah, I had a quick question.
Yeah.
So if the conjectured BPP equals P, then do the quantum speedups, like the exponential speedups, do they go away as well? Or are there some known like lower bounds or for polynomial algorithms? Yeah.
I was going to talk about this later, but for you complexity theorist nerds, this is how these are the conjectured relationships between the standard complexity classes. So we have P over here. We then will have BPP, which is potentially larger. We don't actually know whether BPP is equal to P. Then, of course, we've got NP, and we've got outside of here P space. So if we look at the class of decision problems that can be efficiently solved on a quantum computer with bounded success probability, that complexity class ends up looking like this, to the best of our knowledge. And this complexity class is known as BQP. So quantum computing is believed to be able to efficiently provide solutions for some problems in NP, which may be outside of BPP. It's not believed that quantum computers can efficiently solve everything in NP, but it's known that all such problems that can be solved efficiently on a quantum computer lie within P space, which is the set of decision problems that can be solved using polynomial space, but potentially exponential time. So those are the relationships between things. And again, the boundaries between all of these are kind of unknown. Even embarrassingly, we don't know whether or not P is equal to P space. But these are very, very strong conjectures for people who haven't seen these before. So we strongly don't believe that these are equal to each other. P probably could very well be equal to BPP, but we don't know that. The thing that we strongly don't believe at the moment is that BQP is equal to BPP. However, because of the fact that BPP is more general than P, that's what really makes it most natural to compare quantum computing to probabilistic classical computing, as in like BPP versus BQP. Does that help?
Yeah, a lot. Thank you so much.
No problem. All right, cool. So let me give you a whirlwind tour then of quantum computing. Now, quantum computing is really, really kind of new. It's nowhere near as developed as ordinary computing is. So there isn't even something that's like a von Neumann architecture for quantum computing at the moment. Everything is on an incredibly low level, like lower than assembly level. So the way that we often end up like thinking about this is we like thinking about computing in the language of quantum computing using the language of Boolean circuits. And for those of you who haven't seen this in computer science, Boolean circuits are a model of computing that really actually is strongly influenced by the circuits used in electrical engineering. So the idea basically is that for this model, what we have is we have a sequence of sorry, I said quantum already, a sequence of gates that we use in order to be able to implement an arbitrary function. And the gates that we end up having are the following. We've got, we can do everything using a NOT and an AND gate. And so the basic idea, it's also convenient sometimes to have an OR gate put in, but in principle, you can make an OR with a NOT and an AND. So the basic idea behind these gates is that they implement functions. And so symbolically, we'll often refer to a NOT gate in this particular form. A NOT gate will take an input, X, this is just a single bit. So this is just some number in Z2, which means it's just equal to 0 or 1. And then over here, it will output the opposite of it. So it'll output its negation, which we can also write as the input exclusive or 1. Okay, so it'll end up flipping 0 to 1 and 1 to 0. The next gate that we end up having in this, in the minimal set at least, is the AND gate. And the AND gate will end up taking two inputs, X and Y, and output the product of those two bits. So for example, this output here, this will be 1 if and only if X equals Y equals 1. Otherwise, the output of AND is 0. Okay. And the fun fact, NOT and are universal. And so what I mean by universal, for people who might not have seen this before, is that imagine we've got some arbitrary function, and this function ends up taking inputs that are n bits, which I'll write as Z2n, and it'll map this just a single bit. So this is just like, imagine this is like a decision problem. You'd like to know whether or not some fact is true, and this function will compute that fact. And so for any function f of this particular form, there exists a sequence of NOT and AND gates that computes f or implements f. Okay, I'm not going to prove it, but it's a standard result that you can look up. Okay, so this at some level ends up describing this computational model known as Boolean circuits, and this model can actually be efficient, is equivalent to a Turing machine. So basically what we can do is we can end up saying that this model is kind of polynomially equivalent to the standard model of computing that we normally think of as being the basis for deciding what's computable and what's not. Yeah, Philip.
Are there any restrictions on F? Like, I mean, what if F is the halting function?
So the halting function in particular, that's only a interesting problem because of the fact that it's obscured by an oracle. So what I'm imagining here, right? Imagine you had like a lookup table. So you had the truth table from all the halting states from this output. Then that function could be directly implemented. But if it's hidden in a particular way, like it is in the halting problem, then it's still uncomputable.
Also, in the halting problem, n can be arbitrarily large.
Correct. Here it's fixed. The other thing I should mention, just as a fun fact, is that quantum computers also can't solve the halting problem, which is a real bummer. It would be cool if they could. But there are many things that quantum computers just, do not have the power to be able to do. But in any case, this is kind of like our default model of computing. And reversible computing comes about. Oh, whoops. No, I meant to do this better. Well, whatever. Okay. Reversible computing. The idea behind reversible computing comes about because of a question, right? And this question is, let's consider the AND gate, right? We have X and Y coming in here. And we have a single bit coming out. But the question is, all right, well, where does that information go? Right? In this case, we've got 2 bits of information coming in, and we have 1 bit of information coming out. How physically do we actually deal with getting rid of this extra piece of information along the way? Now, what we actually have to do physically in order to be able to deal with this is we've got to kind of take this extra bit of information and throw it away by putting it into the environment, okay? And it's this act of throwing away information from irreversible gates like the AND gate that actually means that there's something physically kind of missing in this ordinary model of computing because it doesn't talk about where all the unwanted information ends up going in the universe. Reversible computing gets around that problem by ensuring that you keep track of every bit of information. So information in reversible computing can't be created or destroyed. Also, as another fact about this, why this is important is Landauer, who used to be at IBM, he ended up proving what's known as the Landauer limit. He said that to erase a bit of information, you need you need an amount of energy equal to kT ln 2. Where here, this is the temperature of the computer. K is Boltzmann's constant. And this will end up giving you the minimum amount of energy that you need at a fixed temperature to be able to apply an AND gate. And so because there's this energy coming in, and energy is a physical resource that you need to spend, you're kind of, anytime you give yourself access to an irreversible operation like an AND gate, you're secretly giving yourself for free some extra energy. So having a computational model that doesn't allow you to have this free lunch of essentially infinite energy that you're getting for free by having this freedom to be able to throw bits away is a step towards a more physically realistic model of computing. So reversible computing does that. And reversible computing, how that ends up working is that works very similarly to ordinary computing, except what we demand is all reversible gates are functions of the following form. So if we have a function that maps Z2 to the n, i.e. n bits, we demand that the output dimension be exactly the same. As in, there's just as many bits coming in as there are coming out. Furthermore, we also demand that there exists a function g such that g of f of x equals x. Okay, so we assume essentially that all the functions that describe the gates that we have in this computational model are invertible. Okay, so now let's just talk about the operations. So what we're going to do is we're going to build up a generalization of these Boolean circuits to this reversible case. Oh, David, did you ask a question? I saw your mouth move and you're on mute.
I'm talking to myself. I'm just thinking, like, you can't get an AND gate or an OR gate in this world.
You cannot directly, but I'm going to show you how to cheat. Okay, so yeah, because AND or OR have a different number of outputs to inputs, it seems very weird, right? Like, how could you end up bootstrapping off of the universality result for Boolean circuits to be able to show that, you can do all computing in this fashion? And the basic idea is what we're going to do is we're going to cheat by throwing in extra bits to keep track of information that we need to be able to do the inverse. So the first gate that we're going to talk about is the NOT gate. Now, David actually rightly intuited here. He didn't mention NOT because I think it was probably obvious to him that NOT is a reversible operation. And the basic idea here is like NOT, right? What it will do is it just flips a bit. It will take 0 to 1, and it'll take 1 to 0, right? So if we take a look at NOT composed with NOT acting on X, this is equal to NOT of X exclusive OR 1, which is equal to X exclusive OR 1, exclusive OR 1, which is equal to X. So this gate maps one bit to itself. So NOT maps Z2 to Z2, and it has an inverse. In fact, its inverse is even itself. So therefore, NOT is reversible. Okay, that's good. But now going on to David's point, which is, okay, well, what about AND? How do we deal with AND? Okay, so if we're dealing with AND, the AND operation, if we end up taking a look at it in terms of the 3 input bits, I'll call this A, B, and C. This is just equal to
Wait,
C.
3?
Yeah, okay, sorry. You're right, I'm skipping a step here. So the way that we generalize AND over here is we normally would have A and B, and we would output A times B coming out there. We generalize this by creating a gate that we call a Toffoli gate. And this Toffoli gate now has 3 inputs rather than 2. It's going to have an input A, B, and now C over here. And the Toffoli gate, how it goes is and we call this TOF, it will output A and B. Those are going to remain the same. And then the bottom bit is going to be C exclusive or A times B. So this over here, basically, the way it works is you can think about this as like a junk bit here. And this over here now on this side becomes an output. And if we begin with C equals 0, then what this gate, the Toffoli gate, will end up computing is it'll compute A and B down into the bottom bit that we have over here. Okay, so this idea of taking a function and adding an extra bit down at the bottom to make it reversible, this is actually a trick that was invented by Charlie Bennett at IBM in the 70s. And this is known as the Bennett trick. And basically the exact same generalization of this is for any F mapping Z2 to the N to Z2, there exists a reversible F that are reversible G that maps Z 2 to the N plus 1 to Z 2 to the N plus 1 such that G of X0 equals X F of X. Okay, and so this is a generalization of this exact same concept that we had above. So here X for this for the Bennett trick, it can be viewed as the union of the bits A and B. So this over here would be X in my notation down below. Okay, and this over here is the function A and B. So we can end up, this is a concrete example of the generalization that Bennett put forward. Now, in order for me to convince you that Toffoli, in fact, is a reversible gate, I have to show you that Toffoli, in fact, has an inverse. And the way that we can do this is actually Toffoli, it turns out, just like this Bennett trick generalization, is actually self-inverse. So we have that Toffoli of Toffoli A, B, C is equal to A, B, C. So another way of seeing this is let's just use this graphical calculus that we use in Boolean circuits and consider feeding the output of the Toffoli gate into the input of the Toffoli gate. Okay, so the Toffoli gate keeps the inputs A and B as the inputs A and B over here. So if we feed it one more time into the Toffoli gate, we'll get A and B here. And down here, we're going to get C exclusive OR AB, because that's what we had before. But now we're going to exclusive OR AB with it again. Now, any bit exclusive ORed with itself is equal to 0. So this guy is just C. So you can see that two Toffolis in a row end up killing each other and end up producing just ABC back again. All right. And so now that's how this ends up working. So the last thing that I want to talk about really quick is I want to sketch how universality works. Okay, so the way universality ends up working is that if we've got an arbitrary function whose truth table we know beforehand, that ends up mapping n bits to 1 bit, then there exists G1 through Gn such that f of x is equal to Gn of Gn minus 1 through G1 of x. So basically what I'm saying here, and these gates we can envision to be taken from the gate library, not an and. So we're going to have some mixture of not and and gates that end up coming up. Just by the definition of universality, because not and and are universal, we can end up using a sequence of this particular form to implement any function whose truth table we know. Okay, so there exists such a sequence, right? So for each GI that's a NOT gate, that GI is already reversible. So for example, if we ended up having this gate sequence just being knots, we already would have translated that particular gate sequence into a reversible circuit. So we wouldn't need to do anything. So the only thing that actually ends up creating a problem in translating this gate sequence into a corresponding reversible gate sequence is all the AND gates. So how do we end up doing this? Is what we do is we say, okay, for each GI that's and add 1 bit and replace with a toffoli. Okay, because the toffoli on the output ends up computing the value of the and here. We can use that extra the extra memory to store the outputs of all of the AND gates as we go through. So this ends up giving us a way of doing that. So when we compose these two, we can end up seeing that there exists a function g that if this is a sequence of n gates, it will end up mapping z to now to the n plus capital N, potentially plus 1 because we need 1 extra to store the final output. Actually, I don't think we need the plus 1. Yeah, I think it's just plus n. That will map to z2 to the n plus n, and g of x 0, 0, where this is some junk bits, where there's n of these that we potentially need for each of the toffoli gates that could arise in this. And this is 1 bit to store the output. Actually, yeah, I guess it is plus 1. Then this ends up mapping to x, some junk over here, and f of x. So this is most of how the sketch of universality ends up working. But there's one other step. I didn't show that the sequence of reversible gates actually is reversible. And it's really straightforward to see why that's the case. The basic idea is that if we've got a sequence of gates that Gn through G1, and these are all reversible, and furthermore, if we're looking at the toffoli, we ended up having that toffoli squared is equal to the identity channel or the identity operation. So i.e. toffoli is self-inverse. So if we take this gate sequence, Gn through G1, and then we're to apply this to G1 through Gn of x, we can end up seeing that these two sequences pairwise invert each other, and they telescope down to just giving x. And so that's how you can end up seeing that the concatenation of a bunch of reversible gates also is invertible. And so therefore, this sequence of gates is capable of reversibly implementing an arbitrary function. Ergo, we've proven universality. So this model of computing is equivalent to Boolean circuits, and in turn is Turing complete. And it gives us kind of our foundation for our first step towards constructing what a realistic quantum model of computing is, because it keeps track of all of the information in the system. The next step that we will need to do is we'll need to discuss the role that probability can end up playing. And then after that, we'll replace our probability distributions on bits with quantum distributions on bits. And then you'll understand everything that you'll need to understand about quantum theory in order to actually be able to design your own quantum algorithms, at least in principle. Okay, so that's it. Any questions?
Yeah, I had a question. So on the slide, then you said that we need n extra bits, but don't we just need 1 extra bit? Like we are just using 1 garbage 0, right? So can't we just read out that 0 to all of them?
Very good question. So the problem that we end up running into is that, let's say we've got like a sequence of AND gates that we need to compute, right? Like say I needed to do like A and B and C instead of just A and B. The problem is that this residual information that we end up needing in the middle, it actually ends up being needed later on. And so it's often inconvenient or extremely expensive for us to be able to delete that information one step along the way, because we'll need it to invert some of the subsequent steps. So for example, you know, like a standard way that we could do this is, let's say I've got A, B, I'll put a 0 down here, and I'll put a C down here, and 0. So the easiest way that we could end up doing a Toffoli gate would, or an AND gate between these reversibly, is we would do this and compute A, B here, right? But now we need to compute A, B, C. So we're going to need to do this here. But now in order to be able to uncompute the AB, if we needed to do that in the middle, we would then have to kind of do another gate over here to uncompute it. Now that can be done in some circumstances. In fact, it's really good practice to do this when you can. But I didn't want to have to argue when you can do this and when you can't, or how aggressive you have to be about reclaiming these garbage bits in the middle. So that's why I didn't compress it, especially because of the fact that, you know, if we're assuming a model like a Turing machine where you've got an unbounded amount of memory, giving ourselves these extra bits is easy. But in principle, in some of these cases, you can trade space and time by using extra gates to revert some of these junk values back to zero, so you can use them for subsequent operations. And again, yeah, it's a space-time trade-off. But for the purposes of the proof, that space-time trade-off that you're alluding to isn't something we need to explore.
Oh. Yeah, thank you.
Any other questions? All right, wonderful. We've gone a little bit over time, so thank you very much for your patience. But I'll have the first homework assignment up over the weekend. And yeah, it'll be covering, the homework assignment will necessarily be covering material that we haven't covered in class yet. But hopefully, at the very least, it'll give you an idea of where we're going. And you can all decide when you feel ready to tackle each of the problems, even if it's before we've officially covered the material. So yeah, well, thank you very much. If you've ever got any questions, just reach out. And also my office hour, feel free to bug me during my office hours on Thursday. Okay, thanks a lot, everybody.